side of these Fourier weight bounds. So he showed that if you have certain bounds for the Fourier coefficients of functions on the hypercube, then you can construct efficient pseudorandom generators that fool these functions. Okay, so to save some time, I'm not going to say anything about these applications today. So what this talk is about are these bounds that Joe sketched yesterday, but in a specific case where you just consider polynomials, but polynomials if you consider the hypercube as f2 to the n, not as minus 1 or 1 to the n. Okay, so to get us all on the same page, what's the Fourier weight? Okay, so as I said, we are on the hypercube as f2 to the n, so the characters look like this. They are products of minus 1 to the xi, not of the xi's. Okay, it's just to fix the convention. Then the Fourier coefficients are expectation of the character times the function, right? These characters form an orthonormal basis, so the Fourier coefficients are exactly the coefficients of the function in their basis. And then you define the level k Fourier rate as the L1 sum of the functions on the kth level, of the Fourier coefficients of the function on the k level. So you sum Fourier coefficients over all sets that have exactly k elements, and you take the L1 sum. Okay, and I guess what Joe showed yesterday is if you have a uniform bound for this quantity, let's say when k is equal to 2, over some class of functions, then you get an efficient procedure to build a pseudorandom generator with which you can quickly compute the expectation of all of these functions. Okay, and yeah, the question of this talk is how large is the Fourier weight in the case of F2 polynomials. And again, the important thing is these are not polynomials on the hypercube as minus 1, 1, but as 0, 1 to the n. So for example, this polynomial of degree 3 that I've written there, it takes x1 and x2 and x3, so it's only one if they are all 1. Then it takes the xor with the other two things. Okay, I think it's clear. Okay, just to make these Boolean functions, we take minus 1 to the p, and then we denote by p the n, the set of polynomials that have degree of minus d in n variables. And I will sometimes just drop the n if things are uniform in n. Okay, the two papers that Joe talked about yesterday, so he talked about two papers by Chattopadhyay, Hatami, Hosseini, Lovett, and Tal, or by two different subsets of them. But essentially, these two papers give two different, slightly different constructions of these pseudorandom generators. And what they need for their pseudorandom generators to work is either they need a bound for the second level, so when k is equal to 2, or to get something more efficient, they need a bound that is exponential in k. For the level k. So they formulate this conjecture in their paper. If you take the level k Fourier weight of a degree d polynomial, you can control it by something like O of d to the O of k. So polynomial in d exponential in k. And this turns out to be pretty hard to prove. So here are the things that I believe are known about that, and that's it. So with Tal, they proved this bound in the case of the first level, an arbitrary degree. So if you take the sum of the level 1 Fourier coefficients of a degree d polynomial, that's always bounded by 4d. And they proved that in general you can find a bound that's independent of n. That's in the other paper. So you can get k times exponential in d to the power k, so this is super exponential in k, but at least it doesn't depend on n. Okay, and then finally there's this this thing you can do for degree 2 polynomials. So for degree 2 polynomials, you can prove exponential growth in K. And I don't know where this is coming from. So they claim in the paper that they can do that. They don't say anything about it except that they mention it somehow. So we found a proof with Sasha of that when we were not aware that they claimed this in that paper. Okay. So the plan for today is I will show you the proof of the first and the third theorem if time permits.
We claim the same constant?
They don't claim a constant.
Okay.
They write down a conjecture like this one, and then they say they can prove it for degree 2 polynomials. But they don't even say that they can prove it. They say that one can prove it. Okay. Okay, so we just go through these two proofs. So there's nothing deep conceptual that I can tell you. It's just cool tricks. Okay, so you want to prove that the level 1 Fourier weight of a degree d polynomial is bounded by 4d. So if you write out, you expand all the definitions, this just means that the sum here is bounded by 4d. For function fp, and fp is minus 1 to the p for some polynomial of degree d. Okay, now a small observation. Okay, by the way, if I'm too fast or anything, just interrupt. There's a lot of text on the slides, and it's a slide talk. Okay, so we have a sum of absolute values. We would like to get rid of the absolute values, and if we just care about the first level, then that's easy to do. So if you have a polynomial on the hypercube and you translate it in the ith variable, then this only changes the ith Fourier coefficient on the first level, and doesn't change all the other Fourier coefficients on the first level, right? Because the maybe I write it down. So this Fourier coefficient fp, let's say f hat I, is just the expectation of minus 1 to the xi times f of x. So if I shift x in the ith variable by 1, it's the same as shifting this by 1 if I compute the expectation, so it just flips this. Okay, so I can just apply some translation to flip all the negative Fourier coefficients to positive, and then I just remove the absolute values. Then this doesn't change the fact that I have a polynomial, so I just want to estimate the sum of the Fourier coefficients without signs. And if I take this definition and I sum it over n, I get that. So that's what we're going to do. Okay, that's exactly the same as before. So we have to estimate, and I prefer to write it as an average without expectations. Okay, so now we rearrange this a little bit. We don't estimate anything, we just rearrange. So in the top line, we have a sum, and inside the sum is this expression s of x, which is the sum of minus 1 to the xi over all the coordinates. So what does this s of x do? Okay, I realize if I put this too far up, you can't read the slides, and if I read it down, you can't see it. So I'll try to do something. Okay, so we have our hypercube, right? It looks something like this. So this is the point 0, and down here is the point that has all ones. Okay, let's just start with this. And then here you have n-points that have one coordinate equal to 1 and all the other ones equal to 0, and so on. Right, here you have n over 2 points. Okay, so this is like 0. So you get the idea. So what this function s does, it evaluates to n up here. Then here it's n minus 2. Here it's n minus 4. And down here it's minus 10. Right? Because up here I'm summing minus 1 to the 1 n times. Here I'm summing it n minus 1 times, and then I have 1 minus 1. So I'm decomposing my cube into these slices. On each slice I know the value of this s, and I can pull it out. And then inside I just write the sum over the slice. The s can be positive or negative, and I actually organize according to the absolute value of s. So I have the positive slice with the plus and the negative slice with the minus. And okay, actually this s always has the same parity as n. So maybe this is a little bit confusing to write sum over all s, but it doesn't matter. Okay, so we have sum over s, and then we integrate by parts. We have a sum of a product. We can take a discrete derivative of one factor and a discrete antiderivative of the other factor. If you take a discrete derivative of s, you get 1. And if you take the antiderivative of a sum over a level set, you get the sum over the super level set.
It's a very strange way to say it, but
I mean,
it's elementary. You don't.
It's elementary, yeah. I mean, it's summation by parts.
You can
Integration by parts.
That's how I think about it. I mean, yeah, so you write this as a difference of the sum where s is larger than or equal to s and the sum where it's larger than or equal to s plus 1.
Yeah.
And
Or you can see that each element in the second sum is summed over exactly as times, and that's
Yeah. Yes, that's the maybe that's the better way to see it.
it's a little more.
Okay, so you see an element x here exactly if it's at least wait.
This is not the main part of the
No, I think I'm not sure if this is what's going on because anyway, so you can massage this expression for the Fourier weight and you get this sum here. Okay. What I have written in the middle of the page is what we had inside our sum before. So this is for fixed s, and we want to compute this. And the way to compute this is you just write down sets u plus and u minus, which are exactly the sets where the summand is equal to 1. Okay, so I just want to put it again. We have our cut of s somewhere, and we have a cut of minus s. So we are summing over the set above s and below minus s. And u plus is the set upstairs where p is equal to 0. So that minus 1 to the p is 1, and we get 1 in the first sum. U minus is the set downstairs where p is 1. So we get minus 1, but the sum has a minus, so we also get 1. This means if we compute the sum, we just get the size of u plus the size of u minus the sizes of the complement upstairs and downstairs. The complement upstairs has the size of this triangle minus the size of u plus, and downstairs we have the size of the triangle minus the size of u minus. Again, if you put this together, you get 2 times the size of the union of u plus and u minus 2 times the size of these triangles. They have the same size, and we write it together. Okay, so if we go back to what we proved on the previous slide and plug this in, we get exactly the sum of the size of the set U, which is the union of U plus and U minus, minus the size of one of these triangles. And there's a factor of 2 that I pull out. Okay, so the goal is to get a good estimate on the size of U. And this is the nice trick. And in the paper they say this is due to Lars Becker. I tried to find his paper yesterday.
So many.
Yeah, but I know which paper. And I found it, but I didn't see I didn't find the trick in the paper. Okay, so the set where we want to estimate the size of is written up there. It's the points here where p is 0 plus the points here where p is 1. And we are going to estimate this by noting that the size of the set is equal to the dimension of the space of functions on the set. And now the trick is, every function on US, you can write it as 1 minus p times a function on the upper triangle plus p times a function on the lower triangle. Because if I'm on the upper triangle and I am in U, then p is equal to 0, so I see only the first term. And if I'm in the lower triangle, and I'm in U, then p is equal to 1, so I only see the second term. Right? So upstairs, 1 minus p is just the indicator function. No, sorry, on U, 1 minus p is exactly the indicator function of the upper half. So I can do this. Okay, and then there's another observation, which is every function on this cap, you can just write it as a polynomial of degree n minus s over 2. So n minus s over 2 is the level if you count from the top. So here n minus s over 2 is 0, here it's 1. So n minus s over 2 is the number of levels. And the space of functions on such a triangle is just the polynomials of that degree. So right here you have the constant polynomials, and then monomials of degree k are exactly the functions that are 1 in one of these points and 0 everywhere else. So it's clear that the monomials of degree k generate the functions on one such slice. And then by induction you get that all the monomials generate all the functions on that. Okay.
So this is a paper where you give the lower bound majority for a circuit with modular gates?
Yeah.
So it's the same.
It is? Okay. Maybe I should be more careful. All right, so then if you write Q1 and Q2 as polynomials of degree at most n minus s over 2, then phi is a polynomial of at most n minus s of degree at most n minus s over 2 plus d, because it's a sum of p has degree d, Q1 and Q2 have degree n minus s over 2, then phi has degree the sum of the two. Okay, so the size of U is the dimension of the space of functions on U. As we just saw, every such function is a polynomial of that degree, so that dimension is bounded by a dimension of the space of polynomials, which is the sum of binomial coefficients, right? Because there are binomial coefficients, many monomials of degree j, and they are bases. Okay, so if we subtract from U the size of this triangle, so remember this is the expression that we had in our sum that we want to estimate. The size of the triangle is the sum of the binomial coefficients up to n minus s over 2. So the difference is the sum of the many binomial coefficients. And that's the important point, it's only d. Okay, so this is the end of the proof. The level 1 Fourier rate is the sum of, is bounded by, okay, it's the sum of the difference of the size of these sets, u of s minus size of the triangle. So if we use the estimate, we get the sum of a sum of binomial coefficients. But in the inner sum, there are only d summons. And now you can count for each j how many choices of S there are, such that j lives inside the range of the sum, and there are at most 2D many, because j has to be between n minus s over 2 and n minus s over 2 plus d. So you just remove the outer sum and write 2D inside. And the sum of all binomial coefficients is 2 to the n. And from our expectation in the beginning, we have a 2 to the n, and we get what we wanted. Okay. So I find this surprising, because it seems like this argument with counting the dimensions is very bad, but it's not. Or maybe it is, and you could get something better. Okay, so that's the proof.
But linear, so do you know any tightness?
I don't know if this is tight.
I mean, not the constant 4, but
Yeah, I don't know anything. No. It might be that something is normal. I don't know.
It's not always 2D. Sometimes it's less than 2D. It's
Yeah, I mean this is a bad estimate somehow. Maybe if
yeah, it's
I mean if n is fairly large compared to d, then this is probably a horrible estimate. So you can get something less than
it's
4.
integral. Maybe it's 3D.
No, but you know it's omega d.
I don't know any examples where this weight is large. Okay, so that was the first theorem that I wanted to show you. Now the second theorem is degree 2 polynomials and arbitrary level. What I'm going to do is I will show you 3 things that are very simple, kind of, and then you will believe me that this works. But probably we have enough time to just do everything. So we want to do some induction, and if you want to do the induction, you have to do some base cases, and one of the base cases you run into are linear polynomials. Now for linear polynomials, this is quite trivial, right? A linear polynomial is a sum of some variables, so if you take -1 to the polynomial, you just get some character. Characters are orthogonal, so Fourier coefficients of a linear polynomial are 0 or 1. So in particular, the level k Fourier rate is always 0 or 1. You're taking some sums of things that are, at least, at most one of them is 1. So for linear polynomials, this holds. For kind of trivial reasons. But still, we need it for the induction argument. Okay, that's the first step. Then the second step is the important part of the proof. So this is a game you can play for degree 2 polynomials, but you kind of can't do it for higher degrees, probably. And that's why you can prove this for degree 2 polynomials, but not in higher degrees. If you take a sum of 4 characters, 1 plus -1 to the x1 plus -1 to the x2 minus -1 to the x1 plus x2. So you have 4 characters, but one of them has a different sign. And the consequence of that is that this expression is never 4. It only takes the values 2 and -2. I mean, this is not obvious, but you can do the computation. You have to plug in 4. In fact, I did the computation. So you can write this as -1 to the x1 times x2 times 2. This is just a fact. I don't know why this is true, but it's convenient. Okay. And so to show you how to use this, I will prove the bound for level 0, which is a bound for the expectation of a Boolean function, but still it shows how this works. So we do an induction argument. If we have only one variable, then the polynomial is necessarily linear. And if you have more variables and the polynomial is linear, then we are also done by the first step. So for linear polynomials, we have the bound. So you can assume that the polynomial is not linear. In that case, you can pick some variables such that their product occurs somewhere in the polynomial, and you call these variables x1 and x2. And then you sort of extract the parts that depend on x1 and x2. So you write your polynomial is x1 times x2 plus x1 times some coefficient which does not depend on x1 and x2, and I call it p1, plus x2 times the coefficient of x2 which does not depend on x1 and x2, plus p0. If p is of degree 2, then p1 and p2 are linear. I mean, they are of degree 1, and p0 is of degree at most 2. And we plug this in, this expression. So our level 0 Fourier weight is the absolute value of the Fourier coefficient at the empty set, which is the expectation, the function times some sign. So times plus or minus 1. So the sine epsilon times the level 0 Fourier weight is the expectation of minus 1 to the p. If you write out p according to what we just did, you get this. And now we compute the expectation in x1 and x2. There are four values of x1 and x2. So you get 1/4 times the value when x1 and x2 are both 0. In that case, it's minus 1 to the p0. If x1 is 1 and x2 is 0, you get p1 plus p0. If x1 is 0 and x2 is 1, you get p2 plus p0. And if they are both 1, then you get all the terms, and you get a 1 from the x1 times x2, so you get a minus in front. And now you have 4 terms. You have basically a sum of 4 characters, and one of them has a different sign. So you can use this identity. Right, so you pull out p0, because p0 occurs in all of these summons. And yeah, I mean, the factors in front of p0 are exactly 1, minus 1 to the p1, minus 1 to the p2, and minus 1 to the p1 plus 2, but with a different sign. And because of the different sign, you can use the identity and replace this by p1 times p2. And the point is p0 plus p1 times p2 is still a degree 2 polynomial. Because p1 and p2 were the coefficients of some variables, so they are degree 1. So the product is degree 2. And the other point is that p0, p1, and p2 are independent of x1 and x2. So we have decreased the number of variables by 2. And otherwise, we have the same kind of expression, and actually we even gain a factor of 1/2. Okay, so we can do induction everywhere. And I mean, one of the reasons why I wrote down the linear polynomials is because I always get confused. I think if I gain a factor of 1/2, then I can prove that this is really small. But of course it's not, because eventually you end up with a linear polynomial and then it's probably 1. Or it might be 1. Okay. So this is for the level 0 Fourier weight. We have proven that the expectation of a Boolean function is bounded by 1. That was kind of useless. But the point is that this works exactly the same if you do level k, right? Okay, so we write our polynomial in the same way as before. And we can choose signs that now depend on the set, such that the level k Fourier weight is the sum of Fourier coefficients times the sign epsilon a. And if you write what the definition of the Fourier coefficient is, it's the expectation chi a times minus 1 to the p. We put the expectation outside of the sum, then we get this expression. And now we split this up. So the argument before used that we could compute everything in x1 and x2. And this sort of becomes, I mean, it's still possible, but it becomes different if the character also depends on x1 and x2. So we want to distinguish cases according to whether x1 and x2 come up in this character or not. Okay, so we have one sum where the set A does not intersect the set 1, 2, so the character is independent of x1 and x2, and we have the other case. Okay, and if the character does not depend on x1 and x2, then we can actually just do exactly the same as before, because the character does nothing. So yeah, we plug in x1 and x2. It's really the same as before. The only difference is we now have a sum over sets A, and we have this character and this sign, but they don't depend on x1 and x2, so nothing changes there. Again, we have a sum of 4 characters, and one of them has a different sign, so we can use our identity. We get a factor of 2, so this is only 1/2 instead of a quarter, and we have a new polynomial, which is p0 plus p1 times p2, but it still has degree d, and it has fewer variables. But this expression is bounded by the level k Fourier weight of this new polynomial. I mean, we have some signs which might not be the signs of the Fourier coefficients anymore, but then it's still bounded by the sum of the absolute values of the Fourier coefficients. And summing over sets, I mean, we are still summing over different sets. So this is still at most, yeah, it's at most the Fourier weight of the new function times 1/2. And now that 1/2 is important because we have more terms. Okay, so what happens if the set contains 1 or 2? So let's say it contains 1 and doesn't contain 2. Then we can just replace the set by the set with 1 removed. I call it A prime. Then we get that the character associated to A is the character associated to A prime times -1 to the x1. And you can just put the -1 to the x1 inside of our p1. We just replace p1 by p1 plus 1, and then we can do the same argument. Right? And now the only difference is that instead of p1, we get p1 plus 1. The other difference, okay. The other difference is that we sum over the set A prime, so we call it typo, and A prime is smaller. A prime has only k minus 1 element. But that's also good because if we had another summand that depends on a level k Fourier weight, we sort of couldn't do induction. So we have managed to also decrease the parameter k, and we increase the number of variables by 2. Okay, so this is bounded by the level k minus 1 Fourier weight of a new degree 2 polynomial. And you can do the same in the symmetric case where 2 is in A and 1 is not in A, and you can also do the same if both are in A, but in that case you get the level k minus 2 Fourier weight.
So if you had A also equals K, you couldn't finish?
Yes, because then I have 2 summands with the level k Fourier weight with a factor 1/2, so in addition, so in total I get factor 1.
So, yeah, so yeah.
I need that the factor in front of the level k Fourier weight is smaller than 1. Okay, because what I get if I summarize this is I get this inequality. The level k Fourier weight with n variables is bounded by level k Fourier weight with n minus 2 variables times 1/2, plus other things, but the other things are at smaller level. Okay, and this completes the proof because if you plug in 1 plus square root of 2 to the k, you get equality. Right? Yeah, so that's this identity. This makes it work, and I don't think this kind of identity exists if you do the analogous thing for hierarchy. And anyway, it's extremely hard to search for these identities.
And this you know it's constant in times?
No, I don't know any examples. I don't even know any examples where this grows. I think if you try to put in some degree 2 polynomials, you always get things that are like less than 1. But maybe Joe knows some examples. Maybe I should ask him.
Maybe it doesn't depend on K. K should.
So you said that you only know this identity for F2.
I only know it for degree 2. So, okay,
For degree 2.
I have this slide. So this is what you would need to do the same for degree 3. So this is like the sum of characters where one of them has an opposite sign. And you would, this takes values at most 6. So you would want to write it as a sum of 6 terms. Then you could do the same argument. But if you count the number of parameters in these, it's not, you can't search for it on the computer. I think I searched for symmetric versions of that. And if I search correctly, there are no symmetric identities like this. But it would probably be better to have some conceptual idea of what one is doing instead of trying to search for identities. Okay, yeah, that's all I wanted to say.